Today's lesson is an intro to graphing in polar coordinates, and we're going to do this primarily as a graphing calculator driven approach. So we're starting off with a very simple equation. R is equal to 7. And we know that that's going to be a circle with a radius of 7. To derive that, square both sides. Replace your r squared with x squared plus y squared, like we did in a recent lesson. 7 squared is 49, and there's your rectangular equation giving us a center at 0, 0, and a radius of 7. All right, to graph polar equations on your graphing calculator, you're going to want to go to mode. We're going to want to be in radian mode, and we're going to want to bump over to polar. Function is what you have most of your graphing experience in. Parametric, we recently just finished. Now we're going to talk about polar. The last one, sequential. That's one of those topics where some years we get to it and some years we don't. I don't see that happening this particular school year with our current pacing. All right, back to the here and now. When you're in polar mode, when you hit the y equals screen, instead of y equals, it's r equals. So we have a real simple equation to type in. R is equal to 7. Well, what does a standard window look like in this mode? So I hit zoom 6. Okay, in a zoom 6 window, your theta min goes from 0 to 2 pi with a theta step of 0.13. So that's very similar to what we saw in parametric, except it was T min, T max, T step. Your X min, X max, negative 10 to positive 10 in both directions. Now, something we've experienced before, that's something that doesn't appear to be a circle. That looks like an ellipse. So anytime we get a graph like this, we want to ask ourselves, is it really an ellipse, or is it a circle that looks like an ellipse? So what we're going to do is, from that zoom 6, we're going to zoom 5, which is zoom squared. Okay, what zoom squared does is it takes whatever window you're in and adjusts the dimensions to give you a squared up, no distortion type of window. So going from a zoom 6 to a zoom 5 in polar mode is going to take you to a window that's roughly negative 16 to positive 16 in the x direction. Sometimes it might be easier to just type in negative 16 to positive 16, get nice clean numbers. That 0.09 is not going to make a visual difference with anything you do. All right, let's take a look at an equation that's got a little bit more going on. The equation this time is going to be 10 divided by 3 minus 2 cosine of theta. Now, in a recent lesson, I don't recall whether it was previous or the one before that, we looked at, well, how could you convert that into a rectangular coordinates, a rectangular equation, rather. We're just going to jump right to the graphing calculator here. Clear out the old equation, 10 divided by, and then we'll have to put that entire denominator in parentheses, 3 minus 2 cosine theta, close. Okay, when you're in function mode and you press this button, you get an X. When you're in parametric mode, you press this button, you get a T. Polar mode, press this button, you get a theta. Sequential mode, which we're probably not going to get to this year, you end up getting an N. All right, so let's take a look at what this graph seems to be. And it certainly looks like it's an ellipse. So is it really an ellipse, or is it an ellipse or a circle that's been distorted to look like an ellipse? Well, this is that same window that's already been squared up. That negative 10 to positive 10 in the y's, negative 16 to positive 16 in the x's. So that really is an ellipse. It's not a circle pretending to be something else. All right, let's explore some things going on here in this window. Calculator defaults to 0 to 2 pi for your theta min, theta max. Most problems, that's good enough. Some problems, it needs to be tweaked. So let's look at a couple what-ifs. What if, instead of 2 pi, we only had 1 pi? What would happen? Well, for this particular graph, we wouldn't have enough information to get the full ellipse. We get a semi-ellipse. Okay, what if we had a bigger than 2 pi theta max? What if we had, say, 10 pi? And we hit graph. Well, the calculator is still doing something because the little wheel is turning up here. But what's it doing? Sometimes it's useful to go to that little line to the left of the R equals and change it to the option that shows the little circle like this. What this does is it shows a tracing effect so you know where the graph is at while it's being graphed. So if I hit graph now, there it completes the ellipse, and the greater than 2 pi, it just keeps tracing and tracing and tracing over what's already there. So the 2 pi, anything more than 2 pi is redundant. It doesn't give us any more information about the graph. All right. Let's talk about, we'll put this back to 2 pi. Now let's talk about the theta step. For most problems, that 0.13 number is good enough. If you're going to type these in by hand, 0.1, good enough. You don't have to go to 3, blah, blah, blah. It's probably not going to make much of a difference. Maybe it makes a minor difference, but 0.1 will probably work as well as the 0.13. Okay, what if we made it too big? What if we say we made it 0.5? What effect does that have? Okay, one thing is, instead of getting a nice smooth curve, it tends to be more jagged. It doesn't look as accurate as it should. Curves that should be smoother do not appear to be smooth. The other thing that tends to happen if it gets too big, a little smudge on my screen now, is it may not close the graph. So it's not necessarily obvious that's an ellipse with that t-step being a 0.5. Right? What if we make it too small? What if we say made it 0.05 and we hit graph? Okay, what you can see is it's graphing slower, but you tend to get a little bit more of an accurate curve. Now that wasn't too bad. What if we made it 0.01? Now it's at the stage where it becomes painfully slow. So what we have here is a trade-off. You want your theta step to be small enough where you're seeing what you want to see in terms of the smoothness and completeness of the curve. But you don't want it to be so small where it's going to take too long to graph. You'll never finish a quiz or test if it's taking that long to get through one particular ellipse graph like this. All right, let's go back to window. We'll make that 0.1. It's close enough to the default of the 0.13 where it'll get the job done rather than resuming what we already have. All right, now similar to what we experienced with parametric curves, learning about how to graph polar curves opens up brand new families of curves we were unable to obtain or would be too difficult to obtain based on our previous graphing knowledge. So this is a reference sheet. I will post this in Google Classroom so you have it to look at either for classwork, homework, quizzes, or tests, or perhaps you'd like to blow it up and make it poster size for your room. That's your call. There's a similar set of references on page 787 in your textbook. I want to mark that. That's my master copy. Page 787 in your textbook has a similar set of references. Some things are a little bit less detailed, some things are more detailed, but it's also got some good information if you want to combine that with this in terms of a really good reference sheet for graphing polars. All right, so one family that we're going to take a quick look at is this guy right here. It looks like it's lemonscape. I have a feeling that's not how you pronounce it. I think it's pronounced some other way, but in terms of just looking at it, it appears as though it should be a lemonscape. That's how you think it might be pronounced. And these are the basic structures to a lemonscape equation. So one particular one that I want to look at would be r squared is equal to 81 sine of 2 theta. What's that guy going to look like? Well, in your calculator, in that r equals screen, it has to be r equals. It's not going to allow us to directly put in an r squared. So what we're going to want to do is square root both sides. And we're introducing an even root that wasn't there to start with, so we have to do the plus minus thing on one side of the equals, which means we're not going to be able to get this in one single equation. We're going to have to make r1 square root of 81, excuse me, sine 2 theta. And then a nice calculator shortcut, we're going to go negative alpha f4. We use that for line stuff way back when, and then choose r1. And when we hit graph, it gives us kind of a tilted 8 or a tilted infinity, whichever point of reference you'd like to think of. What would happen if we didn't have both equations there? So what if I de-highlight our negative r1 and we hit graph? We don't quite get the complete infinity symbol here. We're missing a piece here, we're missing a piece here. So to get the full thing, we're going to need both. And what happens is we end up getting some redundancy. There are some points that get traced by both the positive and the negative, and then there are some points that get hit by one but not the other one. But to get that full shape, we need to have both the positive and negative of that root. So that lemonscape, or whatever the correct pronunciation is another family of graphs that get opened up in the polar world. All right, next one we're going to look at is this Archimedes spiral is how it's named here. Some books and websites refer to it as the spiral of Archimedes. Either one is correct. For this here, we're back to a very, very simple equation. This r is equal to theta. And in the graph, and you see we get the start of the spiral. This is a good example of 2 pi not really being enough for what we'd like to see. We would like to see this spiral go around more than what it has so far. So what I'm going to do is go to Window, and what if we made it 4 pi? Hit graph. Okay, let's go even bigger. We'll go Window, make it 10 pi. So now we're filling up our entire screen and then some with that spiral design. What if we wanted a tighter spiral? Well, if we give it a coefficient less than 1, say for example 0.5, that'll tighten that spiral up. What if we want it to be bigger or a wider spiral? What if we did say like 2 theta? Oops, I did something wrong. Let's get out of there. Graph, and that widens it up a little bit. All right, another type of spiral called, it looks like Fermat. It's actually pronounced Fermat. That one I know for sure because I know other things about what this guy's done mathematically. For this one, it's r squared is equal to a squared theta. So this is another example where we're not going to be able to get the whole spiral or the whole graph in with a single equation. So it's going to be r is equal to plus or minus the square root of a squared theta. And the one we're going to do as an example here is r squared is equal to 4 theta. R is equal to plus or minus the square root of 4 theta. So square root 4, put that out, start over. Square root of 4 theta, and then do negative alpha f4 r1 in a graph. So this is a pretty cool looking graph if you have a color graph, because you can see in this case the red and the blue blending together. So we kind of get two spirals that work within each other. The Fermat's spiral is not on this reference sheet. I'm not sure if it's referenced in your book or not, but you can learn more about it if you're so inclined by Googling it. We didn't quite fill up the screen here. 10 pi got us pretty close. If we wanted to see this spiral go all the way out to the edges, we could increase our theta max to include a little bit more of the graph. But I think for the purposes of what we're trying to accomplish today, that's good enough. All right, didn't really plan out my space very well in this paper. Sorry about that. All right, next family we're going to go to are the Rose curves. And Rose curves, sometimes they block them all together as like one category. Sometimes they're specific whether your n is even or odd. The n is referring to that coefficient in front of the theta. So one possible Rose curve we could examine would be r is equal to 8 cosine of 2n. So I'm going to go to y equals, clear this out, and put in 8 cosine 2 theta. Ooh, that's theta, not n. I apologize. Cosine of 2 theta. The n is 2, if we're going to go refer to the formula. And we don't need the 10 pi with this. Just going to go back to the default of 2 pi. And hit graph. So we end up getting a Rose curve, and each one of those loops is known as a petal. So this is a 4-petal Rose curve. What if we did r is equal to 8 cosine of 10n? Let's go back and make that 2 a 10. Hit graph. Okay, if we count all those up, turns out that that's got 20 petals. And that's kind of jagged looking. Definitely didn't look pretty graphing. And those don't appear to be petals, they appear to be spikes. So this is an example where that default of 0.1 really is not giving us a good picture of what we're trying to graph. This one is much better as a, say, a 0.05. Cut that in half in terms of the t-step. And you see we get a graph that's much smoother, much prettier, much more rose-like than what we were just looking at. Now still we got some points on the edge, so maybe you want to go even smaller, maybe you want to go to a window, say make it 0.02. You don't even have a smoother curve. That's looking pretty solid. Those are nice smooth petals at the end. All right, so the purpose of what I wanted to accomplish with you guys today is introduce how do you get graphs in polar mode on your calculator, and also give you an idea of what are some different types of graphs that you can get that we were either unable to get or would have been able to get, but it would have been a whole lot more work in other graphing modes. Now, the first one we did is a circle. We've certainly seen that before. The ellipse, we've certainly seen that before. But moving on to the lemon-skate, the spiral of Archimedes, Fermat's spiral, and the rose curves, those are definitely new. We have not seen those before. If we did, it was like a one singleton. We didn't really give it much of a thought. So, as I said, we've accomplished what we wanted to accomplish. Basically, how do you do this stuff on a graphic calculator? Introducing some new types of graphs, and then these guys will be included in one way or another on tonight's homework, which I believe will also be tomorrow's classwork to finish that up as well.